Let's get going. I think we have about 45 minutes to talk about energy density. Um, with really with any manufacturing process, but particularly with additive manufacturing processes, it's important to be able to to uh, to set the machine parameters that we can control so that we get a part with the appropriate properties and with the appropriate features. Uh, and so, and there are typically is more than one machine parameter that needs to be set. And for example, with directed energy deposition, and also with powder bed with the energy sources, there typically are 4 or 5 really important ones that operators have determined. So clearly, the power of the energy source is important. The speed with which the beam moves is important. That's V. The size of the beam can be important. The beam size, D. And the hatch spacing can be important, which is the amount of overlap between progressive scans of the part. So typically there's some overlap to make sure that the energy is dispersed everywhere. And then finally, lambda, the layer thickness, can be important as well. So for years we've understood that these are the important parameters, and so the question then is we can typically form these into all the 5 of them into a single parameter, and historically with additive manufacturing of metals, again DED and powder bed, for the fusion processes, we have a thing called an energy density, and it's always equal to the power of the energy beam divided by some function of the other parameters. What that function is depends on your assumptions, and so there are a variety of forms for energy density, and I want to go through and talk about those. And basically, sort of the punchline is at the end of the day, we want to use the form that gives the best results, right? And then we can ignore the others. But let's look at these. Again, these are the main parameters that we look at. And again, what it does is other than helping us to set the machine properly, it also helps us understand the interrelationships, because if I know the function, it turns out, for example, maybe I can increase the scan speed and build parts faster, but it tells me what other parameters I need to change and by how much in order to maintain the same energy density. Where presumably, if I have an energy density value that works for whatever I want, for good mechanical properties, say, or high strength in the part, if I can establish the critical energy density, then I have the ability within limits to change these around as long as I keep the same overall value for the energy density. So let's look at some of these. The first one, it turns out there are 5 forms that have been developed in the additive community over the years. And I want to go through those with you. The first is a macroscopic volume-based energy density. So the units is typically an energy per unit volume. So it's how much energy am I dumping into the material. And and that's a certain constant amount. If it's acceptably high, then I can get good parts. So basically, one way to get this is the way the derivation works is I take the total energy that's imparted to the part during the build, and I divide by the volume of the part, and that gives me a certain amount of energy divided by the volume. So we can do it fairly easily with a simple cuboid. If I have a cuboid that has dimensions A, B, and C, I can work with this. The total energy that is deposited during this build would be equal to the power of the laser or the electron beam, or I guess it could be even the power associated with the arc, times the time that the part is being built, right? So the power for this equation, the power is easy. The question is, how do we calculate the time that the beam is on and depositing energy? And so that's the hard part of the calculation, but it's not too difficult. What I can do is to scan one layer of material. It's basically it's the surface that I'm scanning, which in this case would be A times B, and then I divide it by the velocity, which is how fast it's scanning. But I also have to also divide by the hatch spacing, because that also impacts the time. So basically, the volume, the scan speed times the hatch spacing tells me how on an area basis how much time is required. So this tells me then this is the time to scan one layer. So I have to determine how many layers there are. That's relatively easy to do. The total build here is C, and if the layer thickness is lambda, then C over lambda will be the number of layers that we need. So armed with this then, I can take the total time required is simply the time to scan one layer, AB over HV, and I divide it by I multiply by C over lambda, the number of layers. So I wind up with ABC over VH lambda, which gives me the volume divided by the scan speed, the hatch spacing, and the layer thickness. And so then armed with that, it becomes relatively easy to substitute this time in this equation. And I have P times time. Actually, the energy density on a volume basis is the total energy divided by the volume, as we set up here. And so I have divided by the scan speed times the hatch spacing. That was his parameter for energy. And so you can see that the difference between this and the first energy term is that the layer thickness is missing, right? So that's the difference. There's another form that's used that we see. In this case, it's really kind of a power density rather than an energy density per unit area. So in this case, it's the beam power divided by its cross-sectional area. Very simple calculation. So it's how much power is being dumped over what area. So it's sort of the intensity of the power that we see here. And so we get this form. And again, here's some examples of some people, researchers that have used this form for to measure the energy density. It turns out we can use the D over V to get the interaction time, and if we substitute this in, we can get the energy density by multiplying this power density by the interaction time, and this reduces to P over VD. So again, comparing these two forms, we see that once again, as was the case for volume energy density, the difference is I'm replacing the hatch spacing with the beam size. And so we have these four forms that sort of parallel each other to some degree. And then there's finally one last form that I wanted to mention, and that's this one. There's a linear-based form, which is perhaps the least popular of these, although you can see there were a few people, I guess one group at least used this. This is a German group. I recognize Eves Christian Hagedorn there. But they simply, again, it's a very simple definition. They simply say, let's take the power divided by the volume and be done with it. And what it gives you is an energy per unit length. So it's not a volume form or an area form, it's energy per unit length. So it would be so many joules per millimeter. So basically you imagine the beam runs along a line, and then along that line, for every millimeter, so many joules are being deposited. Right. So it kind of makes intuitive sense, but it's not very popular. So if we look at these, we have these five forms, and there's a commonality to all of them, and that is they all involve the power divided by the velocity. So power over scan speed is the same for all of these. So what that means, one impact of this is, you might be concerned, like I was at one point. It's like, how are we going to be able to really deal with all these different forms that are out in the literature? Well, it turns out that if the only thing I vary is the power and the scan speed, which are the parameters easiest to vary. The beam size is almost never varied. D is pretty constant. The layer thickness at lambda is also rarely changed. It's more or less constant. And so then if I say, okay, let me not mess with the hatch spacing, then it turns out that all of these will give the same answer if H, D, and lambda are constant. And I'm only affecting the power and the velocity. And so it doesn't matter which one we use, they all give good results. So anyway, so that's the plus side. I actually did some work and published a paper. It was done with nylon, not with a metal. But to ascertain which of these is really the best. And in this case, I varied the beam size and the diameter and the layer thickness so that we could see and probe more completely which of these was doing the best job of predicting good density and good mechanicals. And so this shows the result. This is the density plot for the macroscopic form. So this is the most popular one, the most accurate form that we see. And this shows a plot for different, I guess it's different particle sizes. And again, this was laser sintering of nylon, but it shows the density. And what we see is what we want to see on this plot is that for a given energy density, I'd really like to have a one-to-one correspondence, right? So you tell me the energy density, I tell you what the density is. And so we see that it really works pretty well. Maybe out here at high energy densities, maybe it works not as well as it does at low energy densities. But it also shows that it's useful, because what it does is, like, say, if I want something that's full density, I may need to go down here, say, to 0.25 joules per cubic millimeter. So it tells me, it shows me what the energy density needs to be set at, you know, by adjusting the individual parameters, you know, the layer thickness, the beam diameter, the head spacing, to get a good part. This shows a similar pot. Again, it's the same parameter here that fits the data the best. In this case, we're looking at the tensile strength of the part rather than the density. And we see that, again, this is the plot of the tensile strength versus the volume energy density. And again, we see that for the most part, there's a fairly good one-to-one correspondence between the energy density and the strength. And furthermore, for nylon anyway, if I were to get something up here at this high strength, sort of the best we can do, say around 15 megapascal, then I need to go up around 0.18, 0.2 of the energy density. So again, we can infer from this that there's a range of energy density where I'm at full strength but not full density, because I have to go to about 0.3 joules per cubic millimeter to get fully dense parts, but I get the full strength at a lower value, around 0.15 to 0.2. And so again, this sort of shows the value of having the energy density plot. I didn't show the other plots for the other four, but basically the results are not as good. And that's the bottom line for that. Okay, so let's move on to this. So because P over V is such an important parameter set, it turns out that it makes sense to do a plot that shows these two parameters, the laser power, or it could just as well be the energy of the electron beam power versus the scan speed. And we produce this plot that has 4 regions. It's a very valuable plot. We see this very often in the literature. The first time I saw it was Jack Booth at Carnegie Mellon University in Pennsylvania did this. It was for DED with electron beams in titanium, Ti-64. And he did a lot of work with these plots and with interpreting it, and really came up with a lot of very insightful observations. But for today, I just want to look at the basics of the plot. Again, it's a very common plot when dealing with, you know, settings and good parts. So the question is basically, what do I have to set my machine at in order to get a good part out? And so there's basically and this is true, I've seen this for many different materials and different processes. This is always the case. It always has this look. There's a central region here where we actually make good parts, and good can be defined by density, can be defined by mechanical properties. Again, it doesn't work for ductility or toughness, but for these other properties, it works very well. And so there's a place where we get good parts. If below here, there's a region where we have so-called fusion errors. We'll talk about these more, if not today, later in the week. I'm going to delve into this in great detail, show you micrographs and what these things look like. But basically, down here, there's just not enough energy to really completely fuse the material together. So we can melt a little bit, but we can't melt enough to create a fully dense material. There's just not enough energy. So again, it's the low energy. It happens all the way across the board. If you don't have enough energy, it really doesn't matter how fast or how slow you're going. You simply can't make good parts. And then up here on the high side, basically if the power is too low at a given scan speed, I have fusion errors. If the power is too high, I have so-called keyhole porosity. We'll talk about this later. It's very common in DED to do this. If the power is too high, this is with a laser beam, it turns out that the laser, if the power gets high enough, the laser undergoes an interaction with the material, with the metal, that's called keyholing. It's very common in welding. And in welding, sometimes they actually take advantage of keyholing to produce deep, thin welds. But it's not a good thing in additive manufacturing. And I'll show you the movies of the effect of keyholing. The problem with keyholing is it creates porosity in additive manufactured parts. And so we call it keyholing porosity. It's because the power is too high, or in some cases the scan speed is, the velocity is too slow, right? And so in this case, we can, if I'm keyholing at a certain power level, I can increase the scan speed and eventually move into the good part zone by doing that. Or, of course, if I'm here in keyholing, I can lower the power and come down this way and move into the good spot to make good parts. And so with fusion errors, it's uniformly increase the power because decreasing the scan speed, it's a much narrower plot typically. Although you could conceivably lower the scan speed to get into the good region. Having said that, we typically like high scan speeds, right? Because we can produce parts faster, right, with a high scan speed. So the last area is balling out here. This happens at really at any power level, but at very high scan speeds. Balling is a term that I coined the term in 1990 in a publication. I was the first one to observe it because, in 1990 there was no commercial machine available. We only had the research machine in Texas for doing powder bed fusion, and so I was very early doing metals. We were the only game in town, and so we were the first to observe this balling phenomenon, which is basically little tiny spheres of metal that sit on the surface, and they're approximately the size of the laser beam, or it happens with electron beams as well. And it turns out what the mechanism is. What happens is when the scan speed gets really high, we basically have the energy beam coming down and it's moving this way. If it's moving really fast, what it creates is it creates a melt pool that's very long and skinny. And what happens with long, skinny melts is surface energy effects tend to take over. We have a thing called Rayleigh instability, which is present in a lot of different areas. But we get Rayleigh instability, and that long stream of liquid metal sort of collapses into little spheres to minimize the surface energy. And so that's what the balling phenomenon is. It ruins the part. And again, we were the first in Texas to observe it and published in 1990. Okay, so for example, there's some other things we can do. So for example, if I construct a line here like this, it's basically a line of low energy density. Because remember, the slope of a line coming from the origin here outward, the slope is going to be P over V, right? And we had all of these technologies, all these forms for the energy density, they're all related to P over V. So what I could do then is, so down here this would be, for example, a low energy density. And then if we came up this way, we would have a high energy density, like that. And so we can see that the energy density, we can sort of learn something from this plot, that the high energy density, as you can see here, doesn't guarantee that you get a good part. And neither does low energy density. As a matter of fact, I could pick an energy density that's in the good part range. But if even though I said earlier that that the advantage of the energy density term is that I can dink with the various parameters, the power, the velocity, the hatch spacing, the layer thickness. As long as I maintain a constant energy density, I should be able to produce equivalent parts. Well, it turns out that was not really true, because we can see here with this more complete picture that if I can make good parts at this energy density, if I increase the power and adjust the scan speed accordingly, so that I have the same energy density, eventually I move up into the keep holding range. Likewise, if I'm making good parts, is go, well, I can lower the velocity, the power. If I lower the power and adjust the scan speed accordingly, so I maintain constant energy density, I can move into this area where I produce highly porous parts that typically have poor geometry or poor properties. So again, it turns out the bottom line is what energy density has done for us is it's led us to the stage where we can produce this plot. And this plot really tells a fairly complete picture about what about where to set machine parameters in order to produce good parts. Where again, good has varying definitions. There's the one last thing that I want to mention about this before we finish up is that let's see, what do I? Oh, this plot is generally done where the output metric is the density. So we want fully dense parts, and so we can operate in this range. It turns out that John Lewandowski at Case Western Reserve, I think it's in Ohio, Case Western was part of a large team that came out of Carnegie Mellon. Tony Rawlett, their faculty member, led the team. But they looked at additive manufacturing and properties. So they looked at density, but also at mechanical properties. And it turns out that this plot, this schematic, is really best suited for density. So this can create parts that have good density. But suppose we want good mechanical properties. This was, I think, the most important part of their grant, is that they discovered that if I want good mechanical properties, I want to be obviously in the good part region, but I want to be right below this line, way up here at the highest possible power. So I want to be in the good zone, but at the highest possible power, if I want to create parts with good, high quality, consistent mechanical properties. And so we want to be, basically what I've learned is that in general, when I look at these plots, this is where we want to be, to create parts with good density and good mechanical properties. And again, we'll come back and visit this. I think there's a lecture coming up, maybe talking about microstructure, and we'll talk about the microstructures that are present in these frames and have some nice videos to show as well. I think it's in that lecture as opposed to the mechanical properties. But anyway, I know it's coming down the track. So, okay, well, we're close to the end. So let me summarize where we are. And again, this is I guess I consider this lecture to be sort of the preliminaries for DED. So the next lecture, I'll talk about mechanical properties in DED. We're going to be completely wholly immersed in directed energy deposition at that stage. So anyway, again, I think it's important to note that there are 7 major categories of additive manufacturing process. Again, according to ISO ASTM 52900, and we've listed those. I said earlier today that all of them were developed around 1987 to 2001, and everything since then has been sort of a variation on the theme. I should mention a couple of things about this. There are a ton of additive manufacturing processes that don't fit these categories. But as we said, again, I mentioned earlier, I sit on this committee. So when we meet, it turns out that we have determined over a long period of time that we're not going to bother to define every single approach that's out there. Because John Smith at some university developed some wacky process that's never going to be commercialized. And we don't want to waste our time coming up with a category for that. So one of the rules we use when we're thinking about the process categories and whether to generate a new one is that it has to have at least some degree of commercialization or commercial success in staying power. Because we don't want to waste our time on a process that's going to disappear whenever the grant funding goes away, right? So that's one of the reasons. It turns out actually there is an eighth process that we're thinking about considering, and we're sort of waiting to see if the company. There's only one company that's actually using this technology. I don't know if that's what the committee thinks, but I preliminarily named it. Let's see if I can remember. Sheet lamination. It's a variation of sheet lamination. It's powder lamination rather than sheet lamination. And what it is, it's a technology. There's a company out producing parts this way. But what they do is they basically spread powder away from the machine onto a layer. They create a layer of powder, and then that layer is maybe lightly bound, but then it slides into the machine and it's processed. And so it's really not sheet because there's no sheet involved. It's not powder bed because there's not really a powder bed either. And so, at least in our discussion so far, as we think about this, is I think the name would be powder lamination as an eighth process. But again, the jury's still out. We'll wait and see. The other thing to note about this, I think I have time to do this. If I jump back to the very beginning here, if we look at these technologies, it turns out that the distinguishing feature of these is really there are two things, two factors that differentiate these processes from each other. One is the shape of the feedstock. So, for example, we see sheets and sheets and powder, appear here. So the feedstock form is one way that we distinguish and differentiate these. The other way is the binding mechanism. So are we using extrusion? Are we using a binder? Are we using a photopolymerization? Are we using directed energy or a fusion approach with the powder bed? So the binding mechanism and the feedstock are typically the distinguishing features of this. So then to jump back here to this slide, it turns out that to give you another example that we dealt with on the committee was HP came out with multi-jet fusion. I think maybe some of you may be familiar with that technology. It's a brilliant technology. I think my own personal opinion is they sort of, I don't know if they did a business deal or if they just stole the technology, but Neil Hopkinson in the UK had this technology that he called selective high-speed sintering, which is where he put down basically a coupling binder like carbon black, and then which can happen very quickly in the layer, and then he simply immersed it with an IR heat source, and where the IR heat source would see the carbon black would get really hot, and so but where there was no carbon black, the material would stay relatively cool. And so basically they could lay the carbon black down powder very quickly into nylon, say, and then they could just plaster the whole surface, and you can build parts very quickly that way because we don't have to scan a laser beam over the entire surface with a scan pad. That's half of HP's process. The other half is they stole from my friend Baruch Kashnevis at the University of Southern California, who had a technology out in the early days called selective inhibition sintering, where basically he would send down, instead of putting down a coupling agent, he would put down a decoupling agent and then blast the part with light or with the energy on a surface basis, and then where the part was, the part would bind together, but where the decoupling agent was, the part would not bind. So multi-jet fusion is really a combination of these two. So HP came to the committee and said, what we're doing is completely different, and we want our own classification. And so so the committee looked at it, and we decided, well, no, you have we think that it fits squarely within powder bed. There's a powder bed, and you're fusing the powder bed. So it seems like it should be powder bed fusion, right? And they didn't like it, but that's the way we went. And the HP, unlike Donald Trump, cannot threaten us in other nasty ways. So we got away with it, I guess. And so we did that. But again, you know, we're not really, the committee is really completely neutral on the number of processes. You know, people have come to me and said, you know, why are there only 7 processes? And, you know, I go, we don't really care if there's 7 or 8 or 10. It's just what makes sense. So anyway, sorry for the long digression there on that. But anyway, the committee is very active. We continue to look at technologies and evaluate them. So anyway, so directed energy deposition, again, we have a power source to deposit and melt the metal in powder or wire form. We talked about some of the advantages and disadvantages. We talked about the energy sources and that the energy density really is a key parameter for to help predict part density and mechanical properties. We talked about that. And again, the energy density approach was really developed for DED. That was what whose emphasis was. And then finally, you know, I think the best form, and indeed the most popular form of energy density is the P over V over H lambda, where H is the scan spacing or the hatch spacing, and lambda is the part, the thickness glare beams. So with that, it gets me to the end. So again, I show my end slide again. I don't think I have to explain it this time, but I guess if there, we have maybe enough for questions.
Thank you, sir. Yeah. Any queries from the audience? So, like, I have some questions. Like, when you consider the energy density, you consider any energy loss because of the laser will not absorb all the energy with respect to the powders.
Yeah, sure, absolutely. the derivations obviously assume that we have adiabatic effects, so you don't worry about energy losses. Okay. Again, as if you note these, all of the forms, they don't really care where the energy goes. It's basically the input energy, and we don't really care about whether it's used to melt the powder or whether it's dissipated in the powder bed or any of that. It's basically the energy going in is that, again, you know, that may or may not be justified, but that's the reality. But again, people are using it. It seems to be predictive. So the fact that it's not accurate physically, nobody cares because it works, right? So, like so many other things.
And like if they want to do some kind of new materials, they want to find out some kind of process conditions, like the laser power and scan speed. In what basis they have to start with the initial experimentations to print to melt the materials.
Yeah, right. Yeah, we called. I assume everyone heard with the microphone heard the issue. We call it dialing in a material when we do it. Again, I'm sure with DED it's the same as with laser powder bed. But you know, at my place, over the years, we would have many organizations and businesses who basically say, we have this material that we want to see how it works. Can you build basically a best effort part, which involves dialing in the materials. So we've done this with several materials. I think the last one were these polyurethane type materials, sort of these elastomers, stretchy elastomer materials, technical engineered polymers, I think they call them. But anyway, the way that we did it, you know, and other organizations may do it differently. What we do is, with the starting point, is we take typically a 1 centimeter cube structure, and we'll lay out in the powder bed in the design. We'll lay out an array of maybe 25 or 30 little cubes in centimeter size. And then what we'll do is we'll start with we keep all the parameters constant except the power, which we can change on the fly. And we'll go from a low power to a high power, which effectively cuts across this plot, effectively like right along here, right? So it cuts across here, so we can see kind of the entire span of process, and we know that we're reasonably sure that we'll hit the good spot, right? The good part area. And so we'll do that run, then we'll inspect the parts or do microscopy or tension testing, whatever we need to do on the parts. to see where the sweet spot is. So that's the way we always did it.
Yeah.
You know, it's nice because you can do one build. And usually, one build will give you your answer. I can tell you industrially, what they do is once they have that information, at least with Harvest Technologies, where David Lee was, the way he would optimize is he would do full chamber builds once he thought he had a good process. And so, you know, full chamber builds could be quite expensive in terms of the feedstock. But he would do that. So he would go through, you know, I think he told me once, he went through, you know, maybe 300 or 400 pounds. So I guess it would be maybe 200 kilograms of powder just to dial in the material. You know, we were too cheap at the university to do that. So, yeah. But anyway, that's the way we did it.
Yeah, thank you.
Yeah, sure. There's another question.
Both laser and electron beam, both laser and electron beam powder bed fusion are the laser and electron beam are point sources. So, what materials are manufactured by electron beam powder bed?
Okay. So yeah, so you're happy with the, I caught most of it, but not all of it.
What are the materials manufactured using electron beam powder bed fusion instead of
versus laser? Yeah, it's a good question. Yeah, so basically there's some materials that work better for lasers and some work better for electron beams. To be honest with you, as I think about it, at least for the commercially viable material, so if we don't talk about some weird material, you know, if you look at the nickel, the cobalt, the steel, and the aluminum, I think for the most part I see them processed both ways. I mean, I don't know, maybe, I guess you can DED aluminum, right? I mean,
Yeah, you can do it, but
I don't think there's really a distinction based on the energy source, right? Yeah. So I think there's no distinction. Again, I guess you can imagine that you know, the big distinction is the coupling, but like I mentioned earlier, you know, we're sort of forgiven, at least with powder beds, which is typically the way additive works with metals. In terms of we get the mechanical coupling effect, which improves with the laser. You know, you don't worry about that with the electron beam, but the laser sort of self-corrects because of the mechanical coupling. So, yeah.
Conductive materials may be better. The electron beam goes conductive materials.
Yeah, you think maybe better,
More better than laser.
better parts, better quality with the electron beam? Okay, there you go. So, yeah, but it's not I guess it's not a material issue. It's everything works better with the electron beam. Yeah. Okay. Sure. Yeah. So you use an electron beam.
Good evening, Professor.
Hello.
We are very privileged to be here,
Yeah, thank you.
to be with your interesting lectures. We are very honored to thank Professor Manjaya for organizing this course.
Yeah.
So the direct energy deposition and powder bed fusion both uses thermal energy for making this. Is there any specific applications or products that are suggested for these different two processes?
Yeah, for each one.
Yeah.
In terms of application space. Yeah, I think so. Yeah, for me, first of all, the distinction between powder bed fusion and directed energy deposition. I think in terms of, and again, this is very broad and very general. That basically directed energy deposition can build with faster build rates, whereas powder bed fusion is perhaps best characterized by the finish of the accuracy of the geometry. Those tend to be the two trade-offs. And clearly, I mean, we could argue you move to laser-based AMDED, you can do better part quality in terms of the geometry. And with powder bed, we can do things to speed up the process by using multiple lasers and other things. But basically, my experience is that with powder bed fusion, it tends to find applications where the parts are have fairly complicated geometry, and we don't care that we're building at a low speed. So perhaps small parts with complicated geometries, maybe make us lean towards the powder bed fusion. Whereas if I have a large part, or I'm not so concerned about the geometry, because again, you can produce very nice parts in DED in terms of quality. But if those are not such a big concern, then I lean towards DED personally. I don't know. We have experts here. Do you guys want to? Anybody else want to join in? Yeah, or maybe you have an observation as well about DED versus powder bed.
Then, further moving, maybe you might have done some experiments and experimental results. And based on your experience, is there any findings that out of these two processes, which process gives less energy, which process gives more energy, so that the process is sustainable one?
Oh yeah, so we're talking about sustainability. Yeah, as I mentioned earlier, solely from an energy perspective. So we're not talking. There are other metrics used in sustainability, like water and waste generation and things like that. But just look at the energy required to make a part. Again, we're a victim of the Kutowski plot, so DED will always win on the Kutowski plot in terms of the energy. Because it's not just the absolute energy, it's the effectiveness with which that energy is used to create part volume. And DED is always better than powder bed in that regard. So one could argue that, at least with respect to energy considerations, it's environmentally friendly to use DED than the laser processes, or laser beam powder bed fusion. Because you want to be able to build fast. That's the key issue. Right. Now I'll try to remember tonight. Maybe I'll pull out a good house supply and show you tomorrow. That'd be good. We can do that, and you can see. Maybe it'll make better sense.
Okay. Thanking the other department for making the platform
Yeah.
for us.
Good. Yeah. Thanks. Thanks so much.
Thank you. Any queries?
Professor, I'm basically from computational methods. I used to work in the finite element method, machinery method, this isogeometric analysis. I'm little involved in the material science, especially in this area. To learn something from this only I have come here. My question is, these days in the numerical simulations in which we extensively work, particularly this functionally graded materials, different material combinations are being considered. So how far this process will help for making such a functionally graded material, like a graded composite materials?
Right. Sure. Yeah. Functionally graded materials is a very interesting area, and it turns out that of all of the processes for additive manufacturing, directed energy density, direct energy deposition is the one I think that's best suited for producing multiple materials. Because what we can do is we can just simply have multiple powder jets of different material, and you just turn them on and turn them off depending on where the scan is, and you can create these parts. Imagine it would be almost impossible to do it in powder bed. I mean, you can imagine. People have worked these with powder bed where you take like a little nozzle you have sort of a matrix material that's the powder bed, then you come back over and deposit locally material, but it's just not very well suited. It's so much easier with DED to do functionally graded materials. I can give you my unsolicited opinion about functionally graded materials. Is I consider it to be, I call it a niche application. And by niche, I don't mean that it's not important, not at all. What I mean by niche is it's very important, but only typically to a small number of people, which, I think this fits that. And then I sort of glibly say, we have enough problems with homogeneous materials without trying to complicate it even more with multiple materials. But having said all of that, DED, there's some beautiful examples functionally graded parts, typically done on a layer basis. Not really three-dimensionally spatially, but rather it's a layer of this material and a layer of a different material and a layer of a different material. But there's there's no reason that DD couldn't do otherwise. But they make good parts. They function the way people hope they would in terms of the technology. So I think it's a very good area for the people that see it as an important. It's a way to solve problems. Very specific problems. Yeah.
Thank you, sir. Yeah, along with that, you can do some lot of numerical aspects with respect to the powder flow, how the powder is interacting with respect to the laser. That's what the major challenging issues they are facing in the laser DVD. Even as well as the melt pool, how your cooling rate is going to affect when the part is going very high and high. That
topology optimization.
That topology optimization is completely in design. But when it considers with respect to
topology
the
optimization can be manufactured by PCI game processor.
yes, definitely, definitely we can do that. Yeah, thank you.